All right. So, right. So now, what's a formal proof system? Right. A formal proof system is a set of rules, and when I've looked at formal proof systems for and or and not and stuff, these are the two set of rules, two different proof systems. All right. This is, man, do those look ugly, right? Do you have any intuition about what those mean? Are you going to use those to build intuition? No. But where did I get these? I got it from George's book. And this is what that they work from, right? And then I have a dear friend who was a graduate student with me, and she is brilliant in logic, and she teaches with these, and they're all called sequent logic, and everything is of the form. Every sentence is the form. The or of the left gives me the and of the right, and she says it's great too. But I don't know. Neither of them give me inspiration, right? So when I started teaching this, I built the purple table and saying, dude, these are what we really use in life. Don't do this other stuff, right? All right. So also, when I heard what people were teaching in 1090, I've heard that people have spent the entire term doing proof systems for and or not, right? And I'm like, an entire term? What did they do, right? And especially since you could do everything by the table, right? If I said, let's just, anytime you have an and or not statement, just brute force it. It might take you 2 to the n time, right? We're instant number variables, but you can do it. We don't have to spend the whole term doing it, right? So that was one argument against doing all of this. And the other argument I had was, well, this is not officially a math class. This is officially a computer science class. And how do computer scientists do it? Well, I told you that they do Horn's clause if they are Horn's clause. And if not, they do a thing called Davis-Putnam, right? And it is true, I didn't learn Davis-Putnam until graduate school, but it's also true that I never took a logic course, ever. So I learned Davis-Putnam in a machine learning course, right? So anyway, so what do we want to do? We want to sometimes have a sentence and say, is it satisfiable? Sometimes we'll have the sentence and we'll say, is it a tautology? Can we prove it's always true? And we could bang it out by a table, or we could do this Davis-Putnam thing. And Davis-Putnam is just some old dead white guy. But what is it? Actually, I don't know if he's dead. My dad's alive. Maybe he's alive too. What is it? Is you set some variable and you step to the left and you say, oh, let's pretend that variable is true. And then you try to solve it under the assumption that it's true, right? And then you backtrack and you go the other direction. And now you set it to be false and you try to prove it, right? And you get a recursive algorithm. And I'm going to assume that you don't really understand recursive algorithms yet. Why? Because I teach them in the 3rd year and they don't understand them. In fact, I wanted to fail all my 3rd year students last term because even on the exam, they didn't understand recursive algorithms. All right. So anyway, that's just, everybody see how this is kind of, we have the sentence that we want to plot to prove. We set alpha to be some variable to be true, and we return to the chart. Are we running? All right. So we could try to prove that a sentence is always true. We could also try to prove that a sentence is satisfiable, i.e., it's sometimes true. And we could do that by table lookup. What is Davis-Putnam? Is it's too big of a space to look at all at once, so you split it. And the typical thing is you choose some variable and you split that variable being true or that variable being false, and then you work on it's kind of like proofs by cases. You work on the two halves separately. And one of the things that I like is that if you think, oh, I don't know that my variable, what variable P is false, right? But I'm going to pretend that it's false. I'm going to go into the mindset that it's false, and that allows me then to simplify other things, right? Oh, and what you split on doesn't need to be a single variable, right? It could be, you could split on some weird statement, and this weird statement is true, and this weird statement is false. So let's go back. You haven't missed too many screens yet. This is the only screen we really had. All right. So, right? How do you start? In fact, the purple table thing. How do you prove those results? Well, we did one the other day. We did one last class where we'd already proven a few things, and then we were trying to prove proof by cases, right? But you can always go back to the table, but the table is too big. So then you can always try to Davis-Putnam, and maybe it can be shorter. All right. And then I thought, well, what's a nice short little proof system if you want a short one? Well, it turns out if you just have these rules, you can do Davis-Putnam. And then if you can do Davis-Putnam, you can do anything, right? Because at worst case, you're doing table lookup. So as I said, I had lots of examples, but we're going to do one. And then hopefully that. Right. So Modus Ponens is, of course, a powerful rule that we need. But before we use it, we need to know that it's true, right? We don't want to use rules that aren't true. So here we can think, how can we prove it? Well, what is it? Oh, here we got it. We're not in. All right. So here's this phi is the statement of Modus Ponens. What does it say? It says, if you know that alpha is true and you know that alpha implies beta, then you know that beta is true, right? So that's the statement of Modus Ponens. And we can, as a statement, it's saying we want to say that in every possible setting of the variables, right? There's only three. In fact, this case, there's only two variables, right? So the table is only of size 4. So it's not all that exciting, right? You could just check all 4 settings and see that it works, right? But here we're going to first choose one of the variables to branch on, and I chose to branch on beta. I don't know, because it's on the right-hand side. In one of the settings, it'll clean things up for us, right? So we could try setting it to true, and so then in our proof, well, our proof rules allow deduction. How do you prove alpha implies beta, right? You assume alpha and prove beta, and suppose we know how to do cases, right? So these are the 2 rules that we know how to do, and so we can do cases, and you start by saying, okay, we're going to have 2 cases. One, in fact, and it's a narrow case. Our 2 cases are alpha and not alpha, right? So usually in cases, you'll set you require an or, right? That there's case alpha and there's case beta, and they both give you gamma. Well, here we don't have the or because we have for free that alpha or not alpha is true, right? All right, so here's our first case is that beta is true, and when we know beta is true, we can plug in beta, and we get that if the right-hand side is true, it's automatically true, right? So there we don't have to look at alpha. And similarly, these are all our build rules, right? Remember our build rules say build/eval. So if I tell you that the right-hand side is true, then that makes the implied true automatically. That's one of them in here. I don't know. Oh, here if I implies, right? So here if I tell you that I don't know, maybe I don't remember that, but it's a various rules. All right, everybody follow that? All right, so then we go over the other direction and we set beta to be false. And if you plug it in, then it's not enough to figure out what's going on. So then I branched again on alpha being false. And so now we kind of, if we know that alpha is false and beta is true, then you can evaluate it out. The whole thing is true, right? And similarly, we can have two cases, right? We have a case of alpha being false, and then within that case, we have a case that, right, case that beta is true, case that alpha is true, right? You guys doing okay? Everybody looks pretty asleep today, right? So now we can use the building rules where we know this and we know this, so we can build up this statement being true in our proofs, right? And then you can do this set, you can do this direction, and again you can have the cases that are being that you can build up to proof, right? So if all you wanted to, I mean, this is a useful technique on a test, for example. If I say, well, I'm always going to tell you how to do it, right? So I'll either say, you got to prove it using certain rules from the purple table, or we can say, well, maybe can you prove it using some sort of data type of thing, right? So you branch. And so then you might not have to do this formal proof, right? This is just those, to keep the formal people happy. If you're just hacking it yourself, this is what you do up here, right? All right, and now maybe this was our complicated tree, and maybe there are more, there are the more variables, and so there's more branches, more, right? And so for each leaf, we prove the case that if x3 is false and x2 is true and x4 is false, then that's a path. P here is a path coming down here. And if this path is all true, then we get our result, right? So what we've done is for each path down the tree, we have the case that if that path is all, we decide that that's true, then we get our results, right? And then how do we conclude? Well, we can say, well, if alpha is true, if alpha gives it to us and not alpha giving it to us, then we have it, right? So we can now go backwards, right? Here we've said, well, if x1, assuming all this stuff here, we're in this assumption, right? Within this assumption, if x1 is false, we have it, and then if x1 is true, we have it, and hence we have it, right? Still within that assumption, right? And so similarly, we can say, well, within this assumption, we have it if x4 is false and if x4 is true. So we can apply the rule, right? And then you can keep applying these rules until you've proved your statement. Right? Does that make sense? And so if when you do this, you have what's the worst case is that you have to get, if you have n variables, then you need a full tree of depth n, right? Because you set all the variables. And so there's 2 to the n leaves. And then what you're doing is table lookup, right? So in the worst case, it will still give you a proof. It'll just be big. And in the best case, a lot of the paths will simplify.